Hello, in this lecture we will find the area of the yellow circle. Uh, we have the semicircle. The center of the semicircle is at point O, and inside the semicircle we have the yellow circle, the yellow small circle, and the touching point between the yellow circle to the semicircle is at point P, or the point of contact between the yellow circle and the semicircle is at point P, and the size of line segment PQ equals to 7 times root 2. Let's define the center of the yellow circle as M. So point M is the center of the yellow circle, and let's connect points M and O together by a straight line. So the line segment MO is actually the radius of the yellow circle. We will call it small r, and actually the line segment MO is the radius of the yellow circle because of the fact that it starts from the center of the yellow circle and ends at point O, that is a point on the yellow circle itself. For that reason, MO is defined as the radius of the yellow circle. Actually, the definition of radius is any line segment inside the circle that starts from the center of the circle and ends at any point on the circle itself. It is defined as the radius of that circle, and we have a line segment MO that starts from the center of the yellow circle and ends at point O, that is a point on the yellow circle itself. For that reason, MO is the radius of the yellow circle. Okay, and actually we have a rule. I will call it rule number 1. So rule number 1 states that if two circles touch each other, either internally or externally, Then their point of contact lies on the straight line joining their centers. So I will read again rule number one. Rule number one states that if two circles touch each other either internally or externally, then their point of contact lies on the straight line joining their centers. So now I will explain the rule in detail. So in our example we have two circles. The yellow circle touches the semicircle at point P. So actually point P is defined as point of contact between the yellow circle to the semicircle. So rule number one states about the point of contact that the point of contact, that is to say point P, lies on the straight line. Point P lies on the straight line joining their centers. So point P lies on the straight line. Which straight line? The straight line that joins the centers together. We have two centers. Point M is the center of the yellow circle and point O is the center of the semicircle. So the line segment that joins the centers together, that connects the centers together, is the line segment MO. And rule number one states that point P is actually on the same straight line that MO is. Or in other words, PMO are on the same straight line. That is to say that if we connect points P, M and O together by a line, then that line will be a straight line. Okay? Again, if two circles touch each other, in our case the yellow circle touch the semicircle internally, then their point of contact lies on the straight line joining their centers. That is to say, their point of contact is point P. Point P lies on the same line that that the line segment MO is, or points P, M and O are on the same straight line. Or we can say that together with the line segment MO, point P creates one straight line. Okay, so point P with the line segment MO together create one straight line. So the point of contact P lies on the same straight line that points M and O that connected by the line segment MO lies. Or in other words, points P, M and O lie on one straight line. Or in other words, PMO is a straight line, and also we can say that PO is a straight line. Okay, so if we connect points P and M together, then we will get a straight line. Or in other words, PMO is actually a straight line. Okay, I will explain again. If two circles touch each other, in our example, the yellow circle touches the semicircle internally, then their point of contact, that is to say point P, lies on the straight line joining their centers. So point P lies on straight line. Which straight line? The straight line that joins points M and O together. So point P lies on the same straight line that joins points M and O together. That is to say, PMO is one straight line. Or we can also say that PO is a straight line. Okay? The point of contact P lies on the straight line that joins the centers together. Okay? Point P lies on the same straight line that joins the centers together. Or point P lies on the same straight line as the segment line MO. Or PMO is one straight line. Okay, so actually we can also say that MP is the radius of the yellow circle because it starts from the center of the yellow circle, that is to say point M, and ends at point P, that is a point on the yellow circle itself. For that reason, MP, segment MP, is defined as the radius of the yellow circle. So actually MO or OP equals to 2 times the radius, yes? OP equals to 2 times the radius of the yellow circle. That is to say, MP equals to the diameter of the yellow circle. Any line segment inside a circle that equals to 2 times the radius of that circle is defined as the diameter of that circle. And because of the fact that the line segment OP is first of all a straight line, and then it is actually equals to 2 times the radius of the yellow circle. It is defined as the diameter of the yellow circle. Okay, or we can say that OP is a straight line, and OP equals to the diameter of the yellow circle. Okay, first of all, from rule number 1 we can deduce that OP is a straight line, and second conclusion is that OP is also 2 times the radius, so OP equals to the diameter of the yellow circle. Okay, so from one side OP equals to 2 times the radius of the small yellow circle, but OP is also the radius of the semicircle, because of the fact that it starts from the center of the semicircle and ends at point B, that is a point on the semicircle itself. For that reason, OP equals to the radius of the semicircle. Okay, OP equals to the radius of the semicircle. So I will mark the radius of the semicircle as capital R, and OP equals to the radius of the semicircle, the semi-big circle. The semicircle is the big circle. So actually from one side OP equals to 2 times the radius of the yellow circle, and from the other side OP equals to the radius of the semicircle. So we can deduce from it that the radius of the semicircle is twice as large as the radius of the yellow circle, because OP equals to OP, so you can put, instead of OP you can substitute it by R, and you can substitute OP by 2 times the small radius. So we can deduce from it that the radius of the semicircle equals to 2 times the radius of the yellow circle. This will be our first equation. So the radius of the semicircle is twice as large as the radius of the yellow circle. Okay, or the radius of the semicircle is twice the radius of the circle itself. Okay, the radius of the semicircle is larger to twice the radius of the yellow circle. Okay, so in the same way we can deduce that OQ is the radius of the semicircle, because line segment OQ starts from the center of the semicircle, that is to say from point O, and ends at point Q, that is a point on the semicircle itself. For that reason, OQ is the radius of the semicircle, and I will mark it as capital R. And actually we have rule number 2 that states that in any circle a radius and the tangent to that radius are perpendicular to each other. So I will read rule number 2 again. Rule number 2 states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So if we have a radius, let's call it R, and we have the tangent to that radius, let's call it T, then the radius is perpendicular to the tangent, that is to say this angle is 90 degrees and this angle is also 90 degrees. So in any circle, a radius and the tangent to that radius are perpendicular to each other. So we actually can implement rule number 2 in our circles because we have a radius, the radius of the yellow circle, that is line segment OP, and we have the tangent to that radius, that is QO. So the radius is perpendicular to its tangent. The radius is perpendicular to its tangent OQ. That is to say, this angle equals to 90 degrees, or in other words, angle POQ equals to 90 degrees. Okay, and also in the same way we can say that this angle also equals to 90 degrees, but it is less important to us. So actually we created here a right triangle. POQ is a right triangle because angle POQ equals to 90 degrees. And I will draw again the right triangle POQ. And we will actually use the Pythagorean theorem in order to find out the value of capital R. that is the radius of the semicircle. First of all, I will write down the Pythagorean theorem. Pythagorean theorem. So the Pythagorean theorem states that in a right triangle, we should remember that the Pythagorean theorem apply only to right triangles. So in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I will read again the Pythagorean theorem. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, for example, if we have the right triangle ABC, then the Pythagorean theorem states that AC square, the square of the hypotenuse in this triangle is AC, so AC square equals to the sum of the squares of the perpendiculars, that is to say to AB square plus BC square. Okay, the sum of the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars. And the sum of the square of the perpendiculars are AB square plus BC square, or AC square equals to AB square plus BC square. So I will draw again the right triangle POQ and will implement the Pythagorean theorem in order to find out the value of the capital R, that is the radius of the semicircle. Okay. I will repeat again that the Pythagorean theorem is true only for right triangles. It applies only to right triangles. So this is our right triangle POQ. Side PO equals to capital R, side OQ of the right triangle equals to capital R, and the size of the hypotenuse, that is to say the size of PQ, equals to 7 times root 2. Okay, so according to the Pythagorean theorem, we can say that PQ squared, the square of the hypotenuse, equals to the sum of the squares of the perpendiculars, that is to say OQ square plus PO square. Okay. PQ square, that is the square of the hypotenuse, equals to the sum of the squares of the perpendiculars, that is to say to OQ square plus PO square. But we know that PQ equals to 7 times root 2, OQ equals to capital R, and PO equals to capital R, so we can put the data in equation number 2, and we okay, PQ square is 7 root 2 square, because PQ equals to 7 root 2. OQ equals to R, so we have R square, and PO equals to R, so it is R square, or 7 times root 2 square equals to R square plus R square. and r square plus r square equals to 2 times r square, and 7 root 2 square equals to 49 times 2. Okay, 7 root square is 49 because 7 square equals to 49, and root 2 square equals to 2, and r square plus r square equals to 2 times r square. We can divide the equation number 2 by 2. We get that so we divided equation number 2 by 2. We got that 49 equals to r square. Now we will take a root out of equation number 2. We'll get that so the root of 49 is positive 7, because the other root that is negative 7 is impossible, because we are talking about radiuses, and a radius of a circle must be a positive number. So we take into account only the positive root of 49. So we got that the value, the size of the radius of the semicircle equals to 7 units. But according to equation number 1, we know that capital R equals to 2 times small r. So we write equation number 1 again here. So this is equation number 1, 2 times small r equals to capital R. But we know that capital R equals to 7, so we can substitute capital R in equation number 1 by 7. So we substituted capital R by 7. Now we will divide equation number 1 by 2. So we got that the radius of the yellow circle equals to 3.5 units, because 7 divided by 2 equals to 3.5. Now we can easily find the area of the yellow circle, because we know what is the size of the radius of the yellow circle. So according to the formula of the area of a circle so the formula for the area of the circle, A is abbreviation for area, equals to 4 pi times the radius squared, but we know that r equals to 3.5 units, so we can substitute r by 3.5 units. First of all, I write down that radius for the first equation so actually in the third equation we substituted r by 3.5 units and we got that the area of the yellow circle equals to pi times 3.5 squared, and 3.5 squared equals to 12.25, so we write it down. Okay, 3.5 squared equals to 12.25, so the area of the yellow circle equals to 12.25 times pi, and we get the answer that the area of the yellow circle equals to 38.48 units. Okay, so pi times 12.25 equals to 38.48, so the area of the yellow circle equals to 38.48 units. Okay, so the area of this yellow circle equals to 38.48 units. Okay, so that is the answer to the question. Now I will summarize the lecture. Actually, we wanted to find the area of the yellow circle. In the picture we have the semicircle. The center of the semicircle is at point O, and inside the semicircle we have the yellow small circle, and we see that the touching point between the yellow circle to the semicircle is at point P, or the point of contact between the yellow circle to the semicircle at point P, and the size of the line segment PQ equals to 7 times root 2. Again, the center of the semicircle is at point O. We defined the center of the yellow circle as point M, and we connected points M and O together by a straight line. MO is actually the radius of the semicircle because it starts from the center of the yellow circle and ends at point O, that is a point on the yellow circle itself. So for that reason, MO is the radius of the semicircle. And actually we have a rule number 1, that states that if two circles touch each other internally or externally, then their point of contact lies on the straight line joining their centers. Okay, so in our drawing, the yellow circle touches the semicircle at point P, so point P is the point of contact. And rule number 1 states about the point of contact that their point of contact lies on the straight line joining their centers. So the point of contact lies on a straight line. Which straight line? The straight line that joins the centers of the yellow circle with the center of the semicircle. So the line segment MO joins the centers together, and point P is actually on the same line as MO, or PMO is one straight line. Okay? Now, rule number 1 states that point P is on the same straight line as MO, as the line segment MO, or PMO is one straight line. Or in other words, if we connect together points P, M and O then by a line, then this line will be a straight line. PMO is one straight line. Okay? So point P, the point of contact, lies on a straight line, on the same straight line that connects the centers together. Or point P lies on the same straight line as the line segment MO. Or in other words, PMO is one straight line. Okay, so according to rule number 1, OP is a straight line, and actually MP is also the radius of the yellow circle, because it starts from the center of the yellow circle, that is to say from point M, and ends at point P, that is a point on the yellow circle itself. For that reason, MP is also the radius of the yellow circle, and as you can see from the drawing, MP equals to 2 times the radius of the yellow circle, or MP, or you can say that OP, that is a straight line, equals to the diameter of the yellow circle. And because of the fact that OP is also one straight line, then we can say that OP equals to the diameter of the yellow circle. But because of the fact that OP is a straight line, we can say that OP is also the radius of the semicircle, because it starts from the center of the semicircle. OP starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. For that reason, it is defined as the radius of the semicircle, because in general, a radius is defined as a line segment that starts from the center of the circle and ends at any point on the circle itself. And that is exactly point OP, that starts from the center of the semicircle and ends at point P on the semicircle itself. For that reason, OP is the radius of the semicircle. We marked it as capital R. So uh, from one side OP equals to 2 times the small radius of the yellow circle, but from the other side OP equals to the radius of the semicircle, capital R. So you can deduce from those two equalities that the radius of the semicircle is twice as large as the radius of the small yellow circle. So capital R equals to 2 times small r will be our first equation, and actually in the same way we can say that OQ is also the radius of the semicircle, because it starts from the center of the semicircle and ends at point Q, that is a point on the semicircle itself. For that reason OQ is also the radius of the semicircle, and we actually have rule number 2 that states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So if we have a radius, we will call it R, and we have a tangent to that radius, then this angle is 90 degrees and also this angle is 90 degrees. And we actually can implement rule number 2 in our circles, because we have the radius of the yellow circle. Segment of O is the radius of the semicircle, and we have also the perpendicular to this radius. QO is the perpendicular to the radius. For that reason, according to rule number 2, the radius we have the radius, and we have line segment OQ that is tangent to the radius. Okay, we have the radius OM, and we have line segment QO that is tangent to that radius. OQ is tangent to this radius MO. For that reason, according to rule number 2, they are perpendicular to each other. That is to say, the radius is perpendicular to the tangent. That is to say, this angle is 90 degrees, or in other words, angle POQ equals to 90 degrees. Okay, so actually we have here a right triangle. POQ is a right triangle because of the fact that angle POQ equals to 90 degrees. So we all draw again the right triangle POQ, and OQ, on side OQ of the right triangle POQ equals to capital R, side PO equals to capital R also, and the size of the hypotenuse in the right triangle POQ equals to 7 times root 2. So actually we can apply the Pythagorean theorem in this right triangle, and the Pythagorean theorem states that in a right triangle the square of the hypotenuse, in a right triangle, according to the Pythagorean theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, so the square of the hypotenuse, in this example, is AC square, equals to the sum of the squares of the perpendiculars, equals to BC square plus AB square, or AC square equals to AB square plus BC square. Okay, so we can implement this theorem in our specific right triangle, and as I have already told you, the Pythagorean theorem applies only to right triangles, and we will implement this theorem in our triangle. We actually got that PQ squared equals to OQ squared plus PO squared, but we know that OQ equals to capital R, PO equals to capital R, and PQ equals to 7 times root 2, so we can put the data in the second equation, and we got that capital R equals to 7 units, but according to equation number 1, capital R also equals to 2 times small r, so we can actually substitute capital R by 7 because capital R equals to 7 units. So in the first equation we substituted capital R by 7, and we got that the small radius equals to 3.5 units, and the area equals to pi times the radius squared, but we know the value of the radius is 3.5 units, so we can substitute R by 3.5 units, and we got that the area of the yellow circle equals to 38.48 units. Okay, the area of the yellow square equals to 38.48 units. Okay, thank you very much.